মনে হয় okay this is where we left off in our last class I think that we set up this demo and right now it's running at a decent FPS. Yeah, it's just that we don't have that many polygons. So what we realized, and even from the system monitor, see there isn't much load right now. But if you go and increase the number of polygons right in here, um, where is that? Number of vertices, we have 10,000 vertices. Let's bump it up to, let's say, 1 million vertices. 1 followed by 6 zeros. And then we won't see that performance anymore. See, the frame rate has dropped down significantly, and if you look at the system monitor, the system is a whole lot busy right now. So this is what we realized, that if you add a lot of polygons that need to be rendered, the system can get pretty busy, and it's quite unresponsive. I mean, to click on a particular window, to move it around, it just feels weird. So today we want to improve things in a different way. Rather than drawing them in a fixed pipeline, like with GL begin and GL end, we will draw it with something called VAO, Vertex Array Object. Okay, so that's going to be the task. But before we get there, I want to change a few things over here, just so things are similar when we move on to vertex array objects. Okay, so first of all, this thing is generating all the vertices right in the at the beginning of the program. It's only doing it once, and as you can see, this it's done in the init part. We do this once, and then when we draw whatever, this draw something, that's when we run a loop and get all the vertices from there, and then print them, well, in form of quads, render them in form of quads. So this is where the number of vertices come into play. Okay. However, when we move on to vertex array objects, we will realize that we can't really work with 2D matrices. It has to be done in a 1D matrix, and that's how it is done. That's how the method arguments are taken. So we need to change this somehow. And this is not really that difficult to understand, really. Let me just bring up a spreadsheet to show you what it really means. So right now the setup that we have is that we have X, Y, and Z indices. And this is vertex number 0, vertex number 1, vertex number 2, 3, 4, 5. Let's say we got 6 vertices that we want to render. And there can be random entries. Okay, so for simplicity, let me say that this is my data set. That I've got 6 vertices kept in a 2D array. And in that 2D array, we have all these indices giving me each of these vertices. So this is vertex number 5, or the 6th vertex, the x coordinates 0.66, 0.41, 0.61, something like this, right? But what I want to do right now is to change this organization. So instead of going with a 2D array, I want to flatten it out so that I have a single array, a one-dimensional array. A 2D array can be thought of as one array inside another array. So for example, in this index number 0, we have one array. In index number 1, we have another array, and so on. Okay, so we want to flatten this out. The way we can do that is like 0.92 will go here, 0.19 will go here, 41 then 0.32. Is this idea clear? So instead of a 2D representation like this, we're going to start off like in this fashion. As you can see, index number 5 points to this value. So somehow we need to figure out how to flatten this out, first of all, and then how we can use that. I mean, we can obviously map this back. Say when we say index number 5, this needs to be mapped to row number 1, column number 3, or column number 2 rather. And do we know how to do this? That given any row column value, can we come up with a index number? So if I give you 1 1, can you make it 4? Or if I give you 4, can you go back to 1 1? Yes, no, or did you not understand the problem? See, let me go a little bit further then. This is a 2D array, right? This much we understand. And this one is a 1D array. What I'm saying is that they're going to be the same. The only difference is that this 1D array is going to be a flattened out version of the 2D array. But to flatten it out, you need to find out a way of mapping. So when we're writing x, y, z, let me rewrite them. This is column number 0, this is column number 1, and column number 2. For any given index, right? 2, 1, this is 2, 1. Row 2, column 1. This is actually 7, entry number 7. So when you linearize that, when you flatten it out, you need to be able to calculate, given 2, 1, can I come up with the number 7? Or going the other way, if I give you index number 8 in a flat array, can you turn that into, say, 2, 2? No? See, in the 2D array, for every row, how many columns do we have? If you look at any row, how many columns do we have there? 3. 0, 1, 2, right? 3 columns. Okay, so when we're here, let's say I'm talking about this one. This one should be mapped to 7, right? Now, coming to this point, how many rows have we passed already? 2. And that number tells us right there, right? To pass 2 rows, how many columns have we passed? 2 times 3. 6. What's the current index? 1. So if you add that, that's the result. So the row number times the columns, I'm writing in uppercase to say that, I mean, that's a constant value because it's a fixed number. For every row we have the same number of columns, 3 columns, and added to that we have the current column number. That's going to be the formula. Okay. This is not going to work. So to write this out, like we are doing, 2 is the current index times the number of columns per row plus 1 gives us 7. And the same thing goes for this one, for example. 2, 2 should give us, what, 8. And we can get that by doing 2 times 3 plus 2. And that actually works for anything. So for example, 1, 0, if you want to find that out. 1 times 3 plus 0, that's 3, and that's what we have. Is this clear? So we can find out a simple formula that converts a 2D index into a 1D index. So basically a 2D array can be flattened out in terms of a 1D array. And that's what I'm saying. Because what we are going to start off with today is that we will have our 2D array flattened out in a 1D array. I mean, there was a good reason why I did it in a 2D array when we coded that in our previous class, that we were randomly generating all these vertices, and I wanted to keep it simple. We have the x, y, and z coordinates, and it's easier seen in this way that we have all those vertices, and for each of those vertices we have 3 coordinates. That was the reason why we did that. However, today this is not going to work because we are going to work with something called float buffer, and it expects that you're going to pass the whole thing in a single array, in a 1D array rather. Okay, so that's one of the things. I mean, we don't have to do this math by ourselves, like the row column value mapped into a single number. We don't have to do that math. It's just that you have to have that in the back of your mind, so that if you need to calculate the XYZ values, you know how to do that. Or if you have the X, Y, and Z values, then you can map to any particular index. It goes both ways. So the other thing, like if I give you 7, how can you tell that that's actually 2, 1? See, right now, what we have figured out already is that 2, 1 should be mapped to 7, right? And now the question is this way, that I'm giving you 7, but I want to get 2, 1 out of it. Okay, so we need to find out 2 answers. One is, how do you find out the row value? What I'm giving you is the index. If you divide the index by the number of columns, that gives you the row value, because for each row you're passing 3 columns. So if you divide 7 by 3, what do you get? 2.333, all right? But I mean, when we do the integer division, we are only considering the integer part, or in other words, we are considering the floor aspect of it only. So that's 2. The other thing is the column value is going to come from index mod columns. Whatever is left is going to come out as the columns. So what we have is the index. Yeah, remainder operation, so we get 1. See, with from 7 we can go back to 1. And that actually works for any other ones, like if you put 8 instead. So if I put 8 instead of 7, I get 2, 2. Is this clear? So I mean, it goes both ways. I mean, it's a simple mapping that you can convert from 2D to 1D, and you can also go back from 1D to 2D. All right. These formulas, they may be coming in handy at some point, but not right now. It's just that we need to convert this somehow. So a few things I'd like to change is, first of all, I don't like to write numbers like this. I mean, I don't really know why I did it right over here. This should rather be written in terms of a constant that can be changed somehow. Because I mean, this value can be used in many other ways. Alright, so we're going to define a number that says constant somewhere up here. So when we say 1 milli, we can just say it over here, and we can change the value and everything changes. The other thing I want to do over here in the init method, I want to make sure that, I mean, this is done only once. Well, that's the reason why we have this init method, and that's fine. However, I want to write another method called setup model, which pretty much handles the model setting up tasks like these, right? So we're going to call setup model, and that's going to prepare all the vertices and everything. It's just that it's refactoring the code in a way that it's more meaningful. So we go into the init method, we do all these stuff, and these are mostly event related or window management related. But this particular call, setup model, will only handle the model, the vertex preparation, and everything else. All right. Right now, I mean, in the previous class, it was simple enough, so it didn't really matter whether we write it in a separate method or not. But I mean, this should be localized in this fashion. More so, in a way that if you have um, models written in files that you want to run your games, for example, and then it loads all the map data for the environment and all the object data from different maps. Yeah, it's also going to read the textures and everything. So a setup model, and you will probably pass the name of the model. It's just going to read it from a file and prepare all the vertices. That's going to be the job over there. Right now, the way we are going to do it, we're not going to read from a file, although we could very much do that. We could write all these vertices in a file, save them, and later on when we run this project, we can just read from that file. That's also very much possible. But to keep it simple, I'm not going that route. It's just saying that, I mean, you could do it in this way as well. Now, in the setup model, the first thing I'm going to do here, I'm still not going into VAO, vertex area object. Before I get there, I want to show you that, I mean, this thing can be done in 2D and 1D. So the things that we're going to change, let me just see. All right, we're fine. So instead of going with a 2D array, if you want to change this, it's going to be a 1D array. And then the total number of vertices is going to be 3 times whatever you have, right? Because for each vertex you have 3 coordinates, x, y, and z. That's why we do it in this way. And then the vertices that you're going to generate, it has all the x, y, and z values. So we have prepared a long 2D array, and now we want to write them in the proper place. So I pretty much gives us the row number, right? How can we get the index value if you know the row number and the column number? 0, 1, 2, these are the column numbers, right? And that's the reason I showed you guys how to do it. See, row times the number of columns per row plus the column value. So if you understood that bit, we can say that these values would be written in terms of things like this. Because I gives you the row number, 3 is the number of columns per row, and that's fixed. Is this clear? And let me rename this just to make sure that it's more understandable. It's a long one, but I mean, it's probably more readable now that we have row number, we multiply that by the columns per row, and we add the index number, which is the column number. And that maps it to a single index. Now that we come back over here, when we are drawing this out though, we run into a trouble because we need to find out the x, y, and z values. Right? We need the x, y, and z values. So how do we do that? We know the vertices and it goes through the whole thing, right? So This time around though, let us go by row again. Each row gives us one vertex, and instead of jumping one at a time, we're going to jump 3 at a time, because once we are done with a row, it means that we are done with 3 coordinates. Okay. And then how do we find this out? What we have right now see, we have the index given as row. So row is the first one, row plus 1 is the second one, and row plus 2 is the third one. Right? So for example, this is row plus 1, and this is row plus 2. And if you can understand that, then it's easy to understand that this is going to be a row, this is going to be row plus 2. And once we're done, like, we're advancing to the next one just by saying row equal to row plus 3. And down here, it's easy enough to replace this to say that x, y, and z values would go down here, and that's it. Okay, so there won't be any visible difference at all. It's still going to be just as slow, and well, this is even worse because no, it's not rendering anything, so it doesn't matter whether it's faster or not. Yeah, I don't know how I managed to do that. We have to read them from the vertex array. Okay, I was just talking about the indices. I mean, the indexes, they don't give us the coordinates. We have to look them up. Okay. So with that, you'd see that it's just as slow, nothing changed. It's just that we have localized something into a setup model, and everything is kept in a 1D array. So far we have only managed to change that bit. But is this clear though? I'm moving into VAO and VBO. It takes a bit of time from a regular polygon drawing style, because it's much easier drawing with GL begin, GL end with GL vertex 3D or 3F. However, with performance stuff like these array creation, you'd have to do a little bit more. So the first thing we have to create is something called a float buffer. And that's from java.nio, Java new IO package. And this is where I get lost, and I think I'll get lost in a few more places, because I don't write this code that much often, so it's not in my head all the time. What I did though, if you go into our GitHub repository, you'd see that there are 2 branches. One I use for class, and the other one I do for my own practice or whatever I wanted to demonstrate, and I call that sketchboard. So basically what I'm going to do here, I've already done before, just to test things out. And well, yeah, this is the part I forgot. How do we create the buffer? The answer is buffer utils.create float buffer. So yeah, I mean, in a lot of places, and also because it involves a lot of different API levels where to get these stuff from, I don't have them memorized. I'd have to look into my code from time to time. So that's a bit of a disclaimer. So we're going to create a float buffer, and we have to give the capacity, how many vertices you're going to put in there. And the vertices is just over here. So this example is pretty simple, the one that I tried over here, compared to what I'm going to do right now. See, there are only 4 vertices. And for each of these vertices, how many entries we got? 1, 2, 3, right? So altogether we have 12 entries. So what we have here is simply going to be the same vertices dot length. And once we have that, we're going to say that in this buffer, we want to put all our vertices. Okay. See, this vertices, it's not float, it's actually double. So let me try. If we got this thing, yes, we do. And we can put them in. All right. And once we have done that, then the next call has to be a flip call. It has to do with the architecture of the system and the way these things are accessed. Whether you access the first index first or the second index first. Well, you guys have done computer architecture, right? So you have a clear idea about MSB and LSB, most significant bit and least significant bit. And also, I guess, about endianness, little endian, big endian. No? See, different systems have different sort of representation at the hardware level. So when we work with integers, for example, integer is a 4-byte number, right? Every int is a 4-byte number. So you could write byte 0, byte 1, byte 2, byte 3 from left to right, or you could go from right to left, byte 3, byte 2, byte 1, and byte 0. So these are two different systems. One is called Little Endian, and the other one is called the Big Endian. Actually, I don't remember which one is which, but I mean, that's the difference. One is called Little Endian, and the other one's called Big Endian. But the way the ALU, the arithmetic logic unit, needs to work with them is different than. For example, I mean, this is a little bit off track, but just to give you an idea, that say I give you two numbers, 1, 2, 6, 5, and 3, 1, 1. If I ask you to add these two numbers, you can do that, right? But where do you going to start? From the right. You're going to start over here, and you're going to go to the left, from right to left. So let's assume that this is the Little Endian, although I may be wrong in here in terms of naming. So if that's the case, the other counterpart says that you're going to write them from the right side, 5, 6, 2, 1, and then you write 3, 1, 1 over here. Okay, the numbers need to be read from right to left over here. And in this case, this is simple. You're going to read the numbers from left to right. However, the addition itself is going to be simpler, because now you can just go from left to right. If I write the numbers in reverse order, then I mean it's easier to handle them in terms of arithmetic operations. So you can just add 5 and 3 and then go to the next number and go from here. So the addition can happen from left to right. But in the other case, for all the arithmetic operations, you have to go right to left. However, they both suffer one way or another. Like over here, reading is easy. You can just read from left to right. Over here, you can't do that. When you read the numbers, you have to read from right to left. So AMD and Intel, they have two different representation at the hardware level. One goes with Little Endian, the other one goes with the Big Endian system. And this is just to tell you that, I mean, we we flip the vertices just for this benefit, depending on the system architecture. I mean, if you need it to be flipped, the vertices are put in the proper way. One of them puts the first index of the array right at the start, and the other one just goes the reverse order, MSB and LSB, where this is placed. Which at this level is not that important. You just need to remember that you have to, when you put all these vertices, you have to flip them, and that's the important message to convey. Now, we need to, when you want to use VAO, vertex array objects, you need to prepare some IDs for them, because with the IDs you're going to call them for rendering. So you have two ID, VAO ID and VBO ID. The IDs with the vertex array object, you can describe your model. You can have all your vertices over here. But those are a little bit complicated, because with each vertex you can have a whole lot of data. Let me give you a quick example from Blender to show you what really is happening. Let us go with a little bit complex model. Let's say we got this monkey. It has a lot of faces and a lot of vertices, right? The the data and the vertex data is not enough to describe this model or to render this model, because if you do so, you're going to get a uninteresting render like this. However, we can add color to this, we can add textures to this. We have learned how to do that, right? We also have noticed that we can calculate normals. So right now, if you render this, it has a lot of faces showing up. However, if you go into smooth shading, it's a lot smoother. If you look at the geometry, we haven't changed anything. If you look at the number of faces here, the number of faces is 500. If I go for the flat shaded, this version, it still says that the number is 500. So we haven't really changed anything, but the object looks smoother. So something is being faked right in here. This is not the right thing. Let me just show you over here. So another example. Let us bring in a cylinder. Right? And you can see all these faces clearly, right? Each of these stripes, they represent one face, one quadrilateral. However, if I just go for smooth shading, things will change. But before I do that, let me just count the number of vertices. 64. Number of faces, 34. That's what we got, right? So hit smooth shading, and the faces, they go away. The whole thing is smooth, right? If you look at the number of faces, it still says 34. Number of vertices, still the same, 64. So how have we achieved this? That's the question. So if you go into edit mode, the faces are still there. Let me show you the normals. See what happens. In our class, we learned how to compute these face normals, right? In the first midterm, we have covered that we can take two vectors and we can do a cross multiplication with that to find out the surface normal. It isn't too difficult. However, what happens with smooth shading is that they're actually computing per vertex normal. So they're trying to find out what's the surface normal over here, what's the surface normal over here. So for each vertex, they're computing a different normal. And how that helps? It's actually, see, these two faces, they share a common vertex, right? So the surface normal says that you go here, the surface normal says you go here. Let me bring in a loop cut to make this point a little bit more clear. Yeah, it's easier explained over here. See, the surface normal over here says you go this way, the surface normal on this face, you go this way. But right in here, this guy follows a path that goes through the middle. Okay, and that's just an average of these two surface normals. So just to show you that one goes here, another one goes here, the one that's the average goes to the middle. So if you just take a surface normal on the vertex level, which is the average of the faces surface normal that it's sharing, then you can actually fake this thing. So with per vertex surface normal, you can make things smoother without increasing the geometry of the object. That's the thing. Why I'm talking about this now is because it's important to understand that it's just not the face data, it's just not the vertex data that you need to be worried about. There can be a whole lot more that you need to render out any single object. So for example, when you export this model, let me do the export as we have done before. Wavefront OBJ, this is nothing new. And let me clutter my desktop some more. So we're going to call this monkey.obj. If I export this object, yeah. So we have this one over here, and if you open this, you'd see we got all these vertices, we got all these faces, but the face data is not plain and simple. It says 65//1, and then it has 2//2, 4//3. See, if you, when you do this export, there is an option that says write normals, write UVs. If you uncheck them and if you export that, let me do that once to show you what happens. We got all these vertex data, right? And when we go down to the face data, see, we have only the index numbers, that these 4 vertices, they will make up a face, or these 3 vertices, they will make up a face. That's the usual thing. However, when you want to include the surface normals for each of these vertices, you can write them down. When you have texture mapping, you can write down the texture coordinates as well, because the other 3D programs that are going to use your model to render them out, they are going to need all those information. How is all these things relevant? Is because we have 2 set of things. When we are describing each and every model, we have 2 things in a way that we are describing now. We have a VAO, and this VAO can have several VBOs, vertex array object, vertex buffer object. And in these buffers, we can store many different information. For example, one buffer can hold only the vertex information. Another buffer can hold all the normal information. Another buffer can hold the texture information. Okay. The way the OpenGL has standardized these things is that for each VAO, you can have as much as 16 different VBOs. Okay. We don't even need that. What we have studied in this course so far will tell you that you need 3 of those. The vertex information, and then the texture coordinates, and also the surface normals. All right, so if you can pass these 3, then we're good to go. And for today's example, we are not going to even bother about the other 2 of them. We're just going to see if we can pass the vertex data and then render them out. Okay, is this clear? So that is going to say that we're going to need only one VAO ID and one VBO ID. However, when you're describing a realistic model, there can be several VBO IDs for a single VAO ID. And this is again when I'll probably get lost, but I'll try. VAO ID, you're going to generate that, and I think it's from OpenGL specification 3.0. We'll see. Yeah, that's that. So we're going to generate vertex arrays, and that's going to give us a VAO ID, but then we'd have to bind that to that ID. So again, let me look at the syntax. Yeah, we generate first, and then we call GL bind vertex array. And this is where you use the VAO ID. And I will leave some gap. The idea is that you bind it to the particular VAO ID, and when you're done working with that, you have to release that. And to release that, the syntax is a little bit weird, but I mean, it's you're going to get used to it. You're going to call the same thing, GL bind vertex array. All right. First of all, I generate a number and I bind the vertex array to that number. That's the syntax. And now I need to release that. I don't need it anymore. Once we're done with it, there will be a few more lines over here. And the way you release that is just saying 0. So VAO ID 0 is a reserved ID. When you say that I want to bind the vertex array to 0, it says that you don't have any vertex array bounded to anything. So this is the release thing. For VBO ID, it goes pretty much the same way, although I don't remember whether this is from 13 or I think it's from 15. Let me see. Yeah, gen buffers. 15, right? Right. So we're going to bind this thing, bind this VBO ID to something called GL15 GL array buffer. Yep. Okay. And I'm switching too much. Let me just grab these things because it's difficult to remember. This is from 30, this is from 15, and now we have another one from 20. Okay, so once you bind the buffer to a VBO ID, just as we have done for the VAO ID, then you need to do two more things. First of all, you have to say what's going to be the buffer data, and the buffer data for us is this buffer, the one that we have prepared over here. And how are you going to draw it? You're going to draw it statically. It's not going to be dynamic. I mean, if your vertex information is changing over time, then it's going to be a different constant that you mention over here. And we need to import this GL20. So the attribute pointer over here is not GL float. Because we have used a different thing. We have used double buffer. And float and double, they differ in size, right? Float is 32 bits and double is 64 bit. So it would matter, the vertex data. And then once we are done, we can let go of this thing. So just as with the VAO, and we're going to do the same thing for VBO, that we're going to reset it, that is no longer needed. Okay. There are quite a bit of things that need to be taken care of. Let us just go through them again. That first of all, we have prepared a buffer is called double buffer. You can also use float buffer if you're using floats there. First of all, we have to create a VAO ID. It's just a number, and you bind that, the vertex array, with that number. So in OpenGL and also with GLFW and in different other systems like GLUT, this is pretty much normal that you write everything in terms of numbers. You give labels to each of them. So for example, when we create a window, how do we refer to a window? See, up here it says private long window. So when you create a window, it generates a number for you. And with that number, you say that I'm going to perform these things. For example, when we are saying that make context correct or which window should close, we're actually passing that number. We're just passing that number. And those of you, how many of you are familiar with Android programming, Android app development? One. All right. Well, I guess it will be useful for you at least. When we refer to any component like a text input or anything, we are going back to our resource file, right? Find view by ID. We say find view by ID, and that's r.id is just a number and nothing else. So everything actually becomes a number in terms of GUI-based systems. In some systems you get to see the numbers, in some systems you don't. But they're all referenced through numbers. That's the thing that I'm pointing to. So this vertex array object, they could have done it in terms of pointers, but it's not really useful because it's not cross-platform that way. Because some languages they have pointer support, some languages they don't have pointer support. But if we can give a index number, like what's the ID number for this VAO, you can use that later on. The same thing goes for VBOs. So basically you create an array, and that's through the gen vertex arrays. You just don't say by yourself that I'm going to start a VAO ID and that's going to be ID number 2. You can't say that. Whatever ID number is free or whatever this OpenGL can manage, they will provide you the ID and you save that for your purpose. So these are the two calls. One is to create a VAO, the other one's to create the VBO. Once those are done, you can store your data in there. See, actually we are storing the vertex data into the buffer, not into the array, right? There are two different things, VAO and VBO. VAO is the bigger thing that holds all the VBOs. And like I said, there can be vertex data, there can be texture data, there can be surface normal data or vertex normal data. And all these things need to be bound to a single VAO. So for now, what we have generated over here, we have generated all these things. The array buffer, we're going to say that we're going to bind the VBO to that array buffer. Then we are going to assign the buffer that we have created to that VBO. And the pointer to that is that, well, there are 3 different coordinates. It's going to start from 0. And we're going to keep double. The last 3 parameters for that, I don't quite remember what were the attributes. Let me just have a quick look at it. Oh yeah, the stride. Whether the false says whether the vertices are normalized or not, whether they're chopped down to a certain level. No, they're not. So this is false. How did I see this? It's not even showing me that now. So let me just have a quick look at the API, because the API will certainly have everything written. Alright, so that's the normalized, which we have it as false. The stride says whether there will be any interleaving, like I have a vertex data and right after that I'll have a normal data. Are they going to be mixed and matched? And then we have a pointer pointing to the what. First component, first generic vertex attribute in the array. Yeah. I don't know why that is needed. Maybe it's needed for C, but not here. So we're going to keep these two things as 0. If it's interleaved, there can be many different other datas, but we are not doing that. Everything is packed into one go. So the stride is set to 0. The pointer, I don't know what's the purpose, but it's set to 0. So if you run this now, nothing changes. Really, like, oh, something has changed. It crashes. So that's new. I think I forgot to create the capabilities. Setup model. Yep. See, here's a problem, and a good thing that it crashed really. The way this thing is running is that we are calling init first, and what happens in init? We create the window, we set up the model, and then we show the window. And after init is done, we go into the loop, and in the loop, like, it keeps on running, and if the window shouldn't be closed, we draw something, we sort the buffers, we pull for events and such. However, the very first line right in here, it says GL create capabilities, and this is something that shouldn't stay there. GL create capabilities is basically checking what sort of capabilities does your graphics card provide, whether it's only able to handle OpenGL 1.1 and nothing else. Okay. So all these capabilities are important because we are using some advanced stuff now. Not really advanced, but I mean at least to API level 3.0. How do we know we use something from API level 3.0? You'd see that there are some methods from GL30 class, and GL30 is actually OpenGL 3.0. So whether you're actually able to use those things depend on your graphics card, whether that OpenGL version is supported or not. So this GL create capabilities call is really in the wrong place because we are creating the model, we're using GL30 stuff before even checking for the capabilities. So this should go before we set up the model or do anything as such over here. So I'll leave it over here, create capabilities, and then run this project. Okay, so still it's the same slow demo. It's not doing anything else. The reason being, we have set up our model, but when it comes to drawing this out, what are we doing? We are still calling GL Vertex 3D, which is a really slow thing to do. And that's why these things are really slow. Okay, we have prepared everything, all these VAO and VBO, these things are prepared. It's just that when it comes to drawing them, we are not using any advanced features. So we need to somehow get rid of this part, which is the slow thing, and replace that with something better. This GL Vertex 3D, it's not even defined in the later releases of OpenGL. Like if you go into OpenGL 4.0, you don't even find GL Vertex 3D anymore. You can't do vertex level operations because these are very inefficient. You really have to rely on VAO and VBOs, and that's all the point of us going through these things. And again, I need to steal a bit of my code. And that goes over here. I'll explain what this thing does. But before I do that, let me just test this out. Turns out that it hasn't improved the performance by a big deal. That's a total drag though. Okay, well, let me explain this and what was supposed to happen. First of all, when we draw this thing, this GL begin and GL end, I've removed all these things just to come up with this part. Whatever vertex array we have prepared for us, we're going to use that. So this time again, see in the setup call, there are two things that we did. We bind our vertex array to a VAO ID, and we bind the VBO ID with another ID. So VAO ID, VBO ID, those things are prepared. And just before we finish this off, we have resetted them to 0 in a way to say that we don't need this anymore. Now, when you do this again, we have to say that we're going to use vertex array VAO ID, whatever ID was prepared for us, and we also want to use the vertex attrib array 0, and that's where all these different VBOs come into play. You have to say exactly where the vertex data is, because one VAO can keep hold of 16 VBOs, and we're going to say that the vertex attributes are coming from the first VBO. When it comes to drawing the array, we're just going to say that, well, all these vertices will be drawn in one go, and that's with quads. Okay, we're going to use quads, and then it's going to start from 0. How many vertices it's going to render? That's going to be vertices.length divided by 3, because the number of coordinates per vertex was 3. Once that's drawn, we have to put everything back to normal. We have to disable vertex attribute array and the bind vertex array. They go back to 0, so those are deselected, because we'd have to draw other vertices as well, other parts of the model or other models altogether. So we have to deselect all that. This is weird though, like, I mean, we should see some performance boost. We don't, not at all. The system is very much laggy still. And yeah, no improvement whatsoever. So my first attempt of trying to improve this thing has failed miserably, no doubt. I actually haven't tested this out to see how much of performance boost we get with VAO and VBO. We should have got something. I don't know why we don't. I have to test this out properly. So I'll look into that. But either way, like, I mean, even if you don't get a performance boost, I mean, this is something you can't do anymore with recent OpenGLs. I'll definitely get back to you to tell you what went wrong in here. Why don't we see this performance boost? But the idea is that, oh, I see. Yeah, it's not only VAO and VBO. There are many other inefficiencies going on over here. The push matrix GL rotate F, we'd have to change that with some shader-based programming. I think that could be the reason. Or if this is something else, I'll have to dig into this and try to find an answer. But so far as I think, I mean, these are the culprits. We'll have to change those things with something called shaders. So I'll see how we can do that. But right now, the premise that I had that this will improve the performance, it's actually not doing that. Okay. But I've at least shown you how to use VAO and VBO. So next class I'll say, like, I'll try to figure out how to make this run faster. Okay.
With the same number of
Well, yeah, definitely with the same number of vertices. I mean, this is just as bad as it was before. Okay, if you look at the FPS, it's 4 or 5 or something. It's really slow. So it hasn't improved at all. So I'll see if I missed anything. Um, but so far it seems like there could be other issues. So I'm not sure at this point. I'm not so sure, and I'll definitely have to look into this. I'm gonna stop recording this and I'll upload this code just as it is, because at least it's using VAO and VBO, and that's something new. All right. Any questions? No. Okay, we got one more class today, and we're going to switch back to Blender for a bit, because I said that for the last few classes we will try some fun stuff, some visual effects stuff. Okay. Before we get there though, to make things realistic, we will see that the Blender render that we have used so far is not going to produce realistic results. So we're going to switch to another render engine. It's going to still be the same tool, Blender, but within Blender you have choices of render engines. So in today's class we will look into something called Cycles render engine. Okay? And that will get us ready for what's coming up. All the camera tracking and motion tracking, and how to replace certain stuff with a 3D model, or maybe change the background with a movie, things like that. All right. So you can shoot your own footage and edit those to come up with fancy ideas. That's going to be the target for the last few classes. Okay.